Yesterday during discussion section, we saw in the discussion section that they have these boxes of gloves. I'm not sure if the intention is that people would wear those during their classes, but on the box it says, it's in French, I don't speak French, gants en vinyle jetables. Sorry for my pronunciation. I think that means gloves made out of vinyl that are disposable. And you can see in the smaller print it says without powder and latex free. And so I wanted to talk about this because I can clearly see that these are made out of vinyl. And whenever I hear the word vinyl, what it means to me is it means this functional group right here. This is a vinyl functional group. You'll sometimes hear me call this vinyl, or I'll talk about vinylic protons, and that means this terminal alkene group. That means vinyl. But just calling these vinyl gloves doesn't tell you what this other thing is right here. So let's go ahead and take a look at that. What are they talking about when they talk about vinyl gloves or some sort of material that's made out of vinyl? There has to be some other functional group on there. What they're talking about is a plastic called polyvinyl chloride. It's a synthetic polymer, and it is the world's third most widely used plastic polymer that's made synthetically. The most common is polyethylene. That's like the plastic bottles that you drink water out of. The second most common polymer is polypropylene. It's a stiffer, more robust form. Those are not made using this method that I'm going to show you here. And so polyvinyl chloride, PVC, is the third most common industrial polymer, and it is made through a free radical polymerization process. So the monomer, the name PVC comes from the monomer. You can see that the monomer here is a vinyl chloride. That's not IUPAC nomenclature. That's very old style nomenclature. I think you would call that chloroethene if you were using IUPAC nomenclature, but we would call that vinyl chloride. And if you take some sort of a flask full of vinyl chloride and you add a catalytic amount of radicals in there, like peroxides and heat and that sort of stuff, as soon as you form a bond, a new bond here with that radical, it'll leave another radical right here, like this. And that new radical will then add to another vinyl chloride monomer and make a new carbon-carbon bond, like this. So you'll keep polymerizing, forming carbon-carbon bonds at these positions through that chain reaction type process. That's free radical polymerization, or radical polymerization, rather. And you end up with this polymer, polyvinyl chloride, that has no vinyl groups in it. So it seems a little bit ironic to me that the name of this is polyvinyl chloride. There isn't a single vinyl group in this long chain. And it is kind of interesting that typically polyvinyl chloride is produced with all of these chloro groups in the stereochemically same orientation relative to each other, like all wedges or all dashes. We call that isotactic, an isotactic polymer when the stereochemistry is either all up or all down. Now, where have you seen PVC before? If it's so common, third most common plastic, zillions of tons per year, well, one of the common places you would have seen this is these white plastic pipes, or sometimes black, that carry water underneath your sinks, or if you're in the buildings where there's pipes above the ceiling tiles. Those are all made out of PVC piping. So when I hear PVC, I'm usually thinking piping. But also, sometimes those plastics are referred to as vinyl. So you've heard of vinyl records before, probably. Those are made out of polyvinyl chloride. Those gloves that you find in the lecture rooms that are placed around, those are made out of vinyl polymer, polyvinyl chloride. There could be some clothes, like a shiny raincoat or something that's made out of vinyl. You'll hear the word vinyl to describe that. So we're surrounded by this polyvinyl chloride. Seems like it's everywhere you look, and it's even in the classrooms where we're having discussion sections. Now, let me just say, before we left off, we just had an exam on Monday, and it was tough. I know it was tough. We had 4 chapters. Remember, our first exam was 1 chapter of material? Boy, wouldn't that be great? And that last exam, which was just all kinds of carbonylic chemistry, adding to carbonyls and nitriles, CN triple bonds, just seemed like a lot of material, and it was. It was an immense amount of material. The the average for the exam, for exam 2, was 62, which is, to me, just seems phenomenal. I think you guys did fantastic on that, just considering how much material that we covered. And pretty big standard deviation there, but I think you guys did a great job on a challenging exam. We just had so many reactions to cover. Our next exam, exam 3, is going to cover enolate chemistry and amines. So chapter 21, we've already finished that chapter. We're covering that in discussion sections. Please go to discussion section and practice that. We're talking about the chemistry of enolates in chapters 21 and 22. And then our last chapter is going to be about amines and ammonium compounds. So we left off talking about aldol condensations, and specifically intramolecular versions of aldol condensations. All of these, remember, involve making some sort of an enolate that then attacks these intramolecular versions, that then attacks a carbonyl that's 5 or 6 atoms away. And you have to learn to recognize these patterns. Enones come from aldol condensations, right? And this 5-membered ring enone comes from an intramolecular aldol condensation. And that's super important. To remember to practice these transformations by working problems, and I think the best ones are in the backs of the chapters. We're going to talk about another type of reaction where you make an enolate and you add that enolate to a carbonyl. And the reaction we're going to talk about is called the Claisen reaction. You make an enolate from an ester, and then you add that enolate to another ester carbonyl, and that makes a carbon-carbon bond. So here you're seeing a version of this reaction, and the recipe for this is you take a big pot full of your ester. So in this case, it's ethyl propionate. It's an ethyl ester there, and it's got alpha protons on it. And we treat this with an alkoxide base. And we're going to be very specific about that, so I'll just go ahead and write the recipe here. It's sodium ethoxide. And then in step 2, we have to do a workup on this. And we've seen a lot of workups in this class for reactions that involve bases or organometallics or hydridoaluminate or reagents. But in this case, we have to work this up using acidic conditions. Now, every single synthetic chemist in the Department of Chemistry has a bottle of 1 molar hydrochloric acid. That's what we use. Nobody bubbles in HCl gas, but I'm just going to write HCl here. So what I really mean is aqueous hydrochloric acid. It's an aqueous solution. Could you use aqueous sulfuric acid? Yes. Are you trying to hydrolyze the ester with the acid? No. You're just trying to protonate something that can't be protonated by water. And I'll talk about that a little more. Now, something interesting is happening here, so let's go ahead and just be clear about what's happening. Clearly, something has dimerized because the molecular weight of the product seems to be a lot bigger than the molecular weight of the starting material. So let's draw out the fact that there's always more than 1 molecule when we run organic reactions. Right? Nobody's ever run an organic reaction by putting 1 molecule in the flask. You know, we've got a flask with 6.02 times 10 to the 23rd molecules, and we shouldn't have to tell you that there's more than 1 copy. But I'll draw those molecules here. And now you can more clearly see that what happened is you made an enolate on one of these, and it seemed to have formed a bond to the carbonyl of another ester molecule. And that means there's going to be an ethoxy group as a leaving group. Let's go ahead and draw out that byproduct that you're getting here. There must be some sort of OET. Let me do this in the black pen here. There must be some sort of ethoxide leaving group here. And the purpose of, I'll get to where the acid protonation step comes in. But you can kind of see where this ethoxy group ends up over here. That acted as a leaving group in the reaction mixture. One of the keys to this reaction is that you have to be careful about your base. Don't ever, ever, ever use hydroxide as a base for this reaction. That's because we already talked about what hydroxide does to esters. Hydroxide will saponify esters and cleave them at room temperature and below. It is a super facile process. So do not use sodium hydroxide for this. You'll notice that we were very careful here, or maybe you wouldn't notice, but it turns out that without you noticing, I was very, very careful to make absolutely sure that the alkoxide base here, ethoxide, matched the alkoxy group on the ester. And if you don't do that, this reaction won't work. You'll get a big mess if you don't do that. So if I've got ethyl esters, I use sodium ethoxide. If I have methyl esters, I use sodium methoxide. You have to make the alkoxide base match the alkyl ester that you're using. So, when you're putting in ethoxide or methoxide or even hydroxide, it would be smart for you to think that, gee, shouldn't that be attacking the carbonyl? I thought alkoxides were strong nucleophiles and strong bases, and that's exactly right. Because if you're putting an ethoxide or hydroxide in, the alkoxide anion, just like hydroxide does, is attacking the carbonyl. But this is the beauty of making sure that the ethoxide base matches our ester. So as long as we have this situation where, as long as these groups are the same, if it's the same OR group here, so let me just go ahead and highlight that. If it's the same OR group, then no problem. Then there's no net effect. Then there won't be any net problem, no net effect of this carbonyl addition. We don't want the ethoxide to attack the carbonyl, but that is happening under the conditions of the reaction. And we don't need to draw it when we draw the mechanism. So if you're wondering why the ethoxide doesn't attack the carbonyl, that's the wrong question. It does attack the carbonyl. The question is, why does it not make any difference? And the reason why is, as soon as you come over here and generate this tetrahedral intermediate, one of those is going to get pushed out, and they're identical. So it doesn't even matter which one gets pushed out. It's going to take you right back to the starting materials you had at the beginning. So we have to be careful, super careful, to make sure your alkoxide anion base matches the alkyl ester. Again, if you use sodium hydroxide, you'll just get cleavage of the ester to give a carboxylic acid, and it will be the end of the story. If you accidentally threw in methoxide base, you would end up suddenly with a mixture of methyl esters, ethyl esters, Claisen products with methyl and ethyl esters. It will be a white, hot nightmare. Okay, let me make one last point about this reaction. I always tell you on my exams, on my problem sets, clearly indicate stereochemistry and the presence of stereoisomers, if any. So I hope you notice here that we did create a stereogenic center that wasn't there in the starting materials, and we have no control over that. So you would actually get this plus the enantiomer in this case. And we'll go ahead and talk about where that stereogenic center arises from. It arises from the aqueous workup. All right, let's go ahead and take a look at this reaction, this Claisen reaction. So here's the starting materials for the Claisen reaction. You've got a ethoxide anion floating around in this massive sea of ester. And these ester molecules, you have to choose your ester so that it has an alpha proton on there. This reaction would not work if you didn't have an alpha proton that could be removed by an alkoxide base. And so the first step is going to be to produce the enolate. So I'll go ahead and deprotonate that. I can draw more than one resonance structure. I'm going to draw the resonance structure where we leave the lone pair of electrons on that alpha carbon. And so that's going to leave this enolate intermediate. It's looking for something to attack. There's that enolate. Now we have ethanol. That enolate could pick up a proton from the ethanol and go right back to starting materials. That's happening. This is an equilibrium. Ethoxide is deprotonating it, then putting the proton back, reprotonating it over and over and over again. And if you'll recall, when we talked about why we use LDA as a preference for us, it's because this does not give you a large amount of enolate. There's only a tiny amount of the ester enolate floating around in solution. Right? The byproduct of this reaction is plus ethanol. We don't really need that for this step right here, but I just want to talk about this equilibrium. Right? At equilibrium, the equilibrium lies about 1 billion to 1, more than 1 billion to 1 in favor of the starting materials. You only 1 out of 1 billion. I'm just getting that from the pKa's. I know the pK for ethanol is around 16. I know the pK for this is about 25, 24, somewhere in that region. So is it 10 to the 9 or 10 to the 10? Who cares? You get the idea. 1 out of 1 billion molecules exists as the enolate. And those enolates, this tiny amount of enolate that you generate, are now surrounded by esters that can be attacked. And that's exactly what happens. You got a zillion ester molecules and just a few of these enolates floating around, and so you start to form carbon-carbon bonds. it looks kind of like an aldol, right? Aldol, you add to aldehydes and ketones. In this reaction, the enolate is adding to another ester molecule. So let's go ahead and draw out that intermediate here. Here's that tetrahedral intermediate. We just added a carbon to that, or added in our enolate to generate this tetrahedral intermediate. And there we go. And so now you can see we've got a leaving group on here. This ethoxide can act as a leaving group. Now we've already talked about the fact that when you have a carbanion, and we didn't really talk about the mechanism for amide hydrolysis, but if you have some sort of anionic atom right here, it can push out an ethoxide leaving group. It could push out a hydroxide leaving group. It could push out a methoxide leaving group. So you already know that you can't use alkoxides or hydroxide as leaving groups for SN2, but this is not SN2. So no problem pushing that out. You can't stop that from pushing out that ethoxide anion, and it regenerates a stable C double bond O. Nature loves carbonyl groups, they're so stable. And so that's thermodynamically favorable to push out that leaving group in order to generate what looks like our product. The problem is, it looks like we're done, right? Why do a workup? The problem is this annoying ethoxide leaving group that just left. That's a strong base. And it turns out, if you'll remember from our discussion of pKa's, that the H's between two carbonyls are so acidic. The H's between two carbonyls, if you're a hydrogen atom that is alpha to two carbonyls, a 1,3-dicarbonyl, you're more acidic than water. And so what will happen, whether you want it or not, is that your ethoxide leaving group is going to deprotonate your product that you just finished making. You don't want it to deprotonate, but you don't get to have a choice here. And so the product of this reaction is this enolate. This is the product of that Claisen process that's floating around. Usually there's a sodium cation floating around with this. And it may look to you like, oh, of course water can protonate that. You can't protonate that by putting it in water. The CH over here is more acidic than water, more acidic than ethanol. The only way we're going to get a proton on that is we're going to have to do some sort of an acid workup on this. Okay, so this is the mechanism for the CC bond formation. Let me go ahead and draw out, if we had a sodium counterion on this, that's a pretty common. Could you do it with potassium? Probably, but nobody does that because it's a little bit more expensive. So this is the product of that Claisen process before you do your workup. So let's go ahead and talk about that workup process. Okay, so if I take 2 molecules of ethyl acetate and I do this Claisen reaction using sodium ethoxide, I'm just going to draw 1 molecule of the ethyl ester because, of course, there's more than 1 or 2 molecules in there. And the product of this reaction is, unfortunately, this enolate that we don't really want right now. We just want to get the protonated version of this. And that's just going to sit there. It will sit there. And it's usually you use sodium ethoxide in ethanol, so it is floating in a mixture of ethanol and ethyl acetate, and the ethanol cannot protonate that. So you can't just I have to urge you to avoid the temptation to try to do an H2O workup. That won't do anything. Right? If you put this into water, that carbanion will just go, it's not going to protonate that. We've got to use acid for the protonation step. I'm going to write HCl here, right? You have to use something more acidic than water, substantially more acidic, and I'll just write HCl, but in fact it's always aqueous HCl, but the H2O is not really relevant there. It's just the fact that you're putting in some kind of an acid. And that proton there from the HCl or your acid conditions, that proton ends up over here where the carbanion used to be. There was already a proton in the beginning, but that's what you need to do, a 2-step process. Step 1, sodium ethoxide. Step 2, HCl workup. And it makes that carbon-carbon bond. And now that you have this 1,3-dicarbonyl, you can make stabilized enolates and do more SN2 type alkylations or aldol type condensation processes. This is a common way to make industrial scale chemicals using dirt cheap reagents. All right, let's go ahead and talk about, maybe this is kind of obvious, I'm not quite sure, but you can do crossed Claisen reactions kind of in the same way that you can do crossed aldol reactions, crossed aldol condensations. If you'll recall, a crossed aldol condensation is when the two carbonyl, the two aldehyde or ketone components are not the same. So you're trying to get one of the two components to form the enolate, and then the other carbonyl compound to get attacked. So the key recipe here for a crossed Claisen reactions is that we need one of these esters to have no alpha hydrogens, right? If one of the esters doesn't have alpha protons, then you can't make an enolate out of it, right? We want only one type of enolate floating around in this reaction mixture. So if you look at this top recipe over here, this first cyclic lactone, a lactone is a cyclic ester, has an alpha carbon, right? That's the alpha carbon, and it has an alpha proton. So we call this proton on the alpha carbon the alpha proton. But you'll notice that this other ester in here, this is called ethyl formate, has no alpha carbon, right? It's like what is this? There's not even there's no carbon atom there. So you can't make an enolate if there isn't even an alpha carbon there. And there's no alpha protons if there's no alpha carbon. So there's only going to be one enolate floating around in this reaction mixture. And that's the enolate derived from deprotonation of this piece. And that enolate will then come in and attack the other ester. So you can do crossed Claisen reactions. If I wanted to get this product, remember it's a two-step process. Look how carefully I matched the base over here with my ester. And now we're going to make this step 1. We're going to have sodium ethoxide. In step 2, we're going to have HCl. We have to use an acid for the workup. Now there's a tautomer thing going on over here with the product, but that's okay if you draw this as a 1,3-dicarbonyl instead of the enol product, which there'd be a lot of that in there. Now, again, let me come back to this same situation with, we could do this over here with two acyclic esters. So I'll take my two esters here, and another common type of reactant used in crossed Claisen reactions would be benzoate esters, because there's no alpha proton over here on this carbon. I'm putting a dot there. There's no protons on that. So there's only going to be one type of enolate floating around in this mixture. And so that's going to be a good recipe for this crossed Claisen reaction. So we're going to have step 1 is going to be sodium, well, it's ethoxide is more common than methoxide, just because ethanol is very inexpensive. And then we follow this up with a workup. Remember that workup, the HCl puts the proton on that stable enolate product. You can't protonate the enolate product using just water. All right, so cross Claisen is pretty useful. Now, the Claisen condensation, making CC bonds with the Claisen, it's not that common, actually. The yields aren't great. The book doesn't really mention that, unfortunately. So let's go ahead and talk about a version of the Claisen reaction that is actually very common and very useful and gives high yields. And that is the intramolecular version of the Claisen reaction. I don't know how things worked 100 years ago, but back then you could just do some trivial modification and, wow, is this screen blinking on you? Because it is blinking up here. Boy, a couple weeks ago, nothing got recorded on the main screen. Okay, so that's awful. I have to come back in and re-record. That's a tough act to come into an empty room and re-record these lectures. Okay, so let's talk about the intramolecular Claisen, which some other person put their name on it. I mean, I don't know why they don't just call it an intramolecular Claisen, but this is called the Dieckmann reaction. I guess because it's more useful. Dieckmann realized, wow, you actually get good yields if you're doing this intramolecularly to make 5- and 6-membered rings. And the basic concept here is, if I make an enolate, it collides very frequently with atoms 5 and 6 atoms away, with carbonyl groups that are 5 and 6 atoms away. And the frequency of that collision drives the equilibrium and the fast rates of this process. So you get high yields and you get fast reaction rates. So here we're going to take two ester molecules and they're attached, specifically attached so that one enolate will be 5 atoms away from another carbonyl. Okay, let's go ahead and draw out our recipe. Step 1, we use sodium ethoxide, and we're matching the ethoxide to the ethyl ester group that's on there. Step 2, we got to follow this up with a workup again, and it's going to be an HCl workup. And this is just going to be an intramolecular version of the Claisen, but the yields are great for this. So in this case, you can see that we're forming a 6-membered ring if you just kind of trace this through. Now, I find that it's hard that people are having a hard time not making mistakes. So I usually try very carefully, if I'm worried about drawing the correct products, to map carbon groups. So over here, I attacked a carbonyl, I'll call that carbon 1, that has no H's on it. That's next to a CH2 group number 2, that's next to a CH2 group number 3, that's next to a CH2 group number 4, and that's next to a CH2 group number 5. So when I draw this product, I'm going to make sure I have the same number of CH2 groups, and I'll number them here. Whoa, why did that just happen? Wow, there's something going on here. This is insane. Wow. Okay. Sorry about that. I don't know what's happening. I don't feel like I'm touching anything special here. Okay, so the carbonyl group is atom number 1. Let me just make sure I've drawn this correctly. It's next to a CH2 group number 2. That's next to a CH2 group number 3. That's next to a CH2 group number 4. That's next to a CH2 group number 5. And this CH2 group over here, number 6, must have been an enolate that got one of the protons removed. And so that's still here, but now a CH2 that used to be 6 is now a CH. It's number 6. So you got to be careful that you're drawing products that map onto the starting materials. Now on my exams, on my problem sets, if I draw a box and I say the products, say draw the product or products in the box, I want you to show where the carbon atoms from the starting material ended up. So in this case, if I draw a box, I would expect you to draw where this red ethoxy group ended up. It ended up here in another molecule of the ethyl ester. There is also a stereogenic center now. Carbon 6 is a stereogenic center. I would expect you to indicate that. I'll go ahead and just make this ester group going wedge here since it's sticking off of the ring. And I'll write plus E. So it looks like a lot of work, but boy, you generate this beautiful 6-membered ring, and you're ready to go back and treat that, isolate it, measure the yield, come back next week, add some base to that, and start making enolates and doing more chemistry. So 6-membered rings are awesome. 5-membered rings are also awesome. And you can, if you plan carefully, you can do kind of crossed Claisen condensations. Intramolecularly, it's still called a Dieckmann cyclization or a Dieckmann reaction. So let's go ahead and take this product here, because this is the kind of question that you'll be confronted with. It'll be, here's a product, how do you make that? And that to me is just screaming Dieckmann reaction or Claisen, or intramolecular Claisen. I see the 1,3-dicarbonyls. See this right here? 1,3-dicarbonyl. Boy, that's Claisen. Right? We're going to make an enolate and we're going to add it to another ester. So we're going to make an ester enolate. That's when I see the 1,3-dicarbonyl, I'm just thinking that. And if it's cyclic, it's a Dieckmann cyclization. Let's go ahead and try to draw out. Can we figure out how to draw out this starting material for this, if that's what we're being asked? So how would we make that? Well, I'm going to have a benzene ring in the starting material, and I'm going to have over here a carbonyl that gets attacked. And then the question is, boy, what's the likely types of starting materials that I could have here? What I'm going to do is I'm going to walk back over here, and I'm going to say, well, this looks like the bond I wanted to form, and so maybe I had an ester group over here, and that would make sense. In this case, it would be an ethyl ester. So let me try to draw that out without making a mistake. So I'll draw over here this carbonyl with that ethyl ester, the OCH3. And then I'll come over here and make sure I'm drawing the rest of these pieces. I have a CH2 group here, and then I have over here another carbon that formed the enolate, a carbonyl, and an OCH3 group. And I'm going to just map these really quickly to make sure I didn't make a mistake, because it's super easy to miscount the number of CH2 groups. So let's just double check here. So I'm going to call this carbon 1. You could call it A, B, C, alpha, beta, gamma. I mean, try not to do that because we use alpha to describe something different here. But I like to use numbers when I do atom mapping. So there's CH group number 2, here's CH2 group number 3, and it's next to benzene ring atom number 4 that has no H's. So I see carbonyl group number 1, I see a CH2 now, which makes sense because we had to deprotonate it to make an enolate. It's next to a benzylic CH2 group number 3, and that's next to a carbon that has no H's on the benzene ring number 4. So that looks good. It looks like it checks out, and it looks like if I did do that Dieckmann cyclization, then it would be the right substrate for that. So that's kind of the way to work backwards here. So let me go ahead and write out the recipe in case that's not obvious for this. It would be sodium methoxide, right? These are methyl esters. We've got a methoxy ester here, so we have to make that match. And step 2 would be HCl workup. And there's no stereochemistry in the starting material, so there's no reason for me to indicate the stereochemistry in the starting material. All right, that's a Dieckmann cyclization or a Dieckmann reaction. It's an intramolecular version of the Claisen, and they're much more efficient than just having two esters somehow collide with each other in a Claisen condensation reaction. All right, we're nearing the end of the chapter, and we're going to talk about 1,4 addition reactions again. Do you remember I put a problem on the midterm number 2 where I was asking about cuprate addition to some sort of an enone. And at the time, I just wondered, why did they jam this here into chapter 17? There was so much stuff in chapter 17 with Grignard reagents and alkylithiums. I didn't feel like it was worth talking about 1,4 addition reactions. But I had hinted at the fact that you were going to see them again. And this is where we're coming back to 1,4 addition reactions, not using cuprates. But of course, I hope you know that you could add cuprates in here to this beta carbon of an enone. But it turns out that stabilized enolates can also add. And what do I mean by stabilized enolates? Highly stabilized enolates derived from 1,3-dicarbonyl compounds are selective for adding to the beta carbon of an enone. So let's go ahead and check this out. If I have over here a 1,3-dicarbonyl compound and I make an enolate out of this, that's a super stable enolate. That will selectively add to the beta carbon. Not to the carbonyl, but to the beta carbon. A regular enolate with just one carbonyl would add to the carbonyl group of the acceptor. But here, this super stabilized carbonyl likes to add preferentially faster to that beta carbon. And I can push the arrows in multiple different ways. If I push the arrow like this, you can kind of see how that works. And then I need to do an HCl workup on this. Why do I need to do an HCl workup? The reason is that the initial enolate here will start to deprotonate. Let me go ahead and draw this out. We'll start to deprotonate over here, and you'll end up with an enolate at the end of your reaction mixture that is so stable you can't deprotonate it. Well, that looks like a little sad face with my lone pair there. I don't like that. Let's make it happy. Let me erase that. I mean, after the HCl workup, there's a proton there anyway. Okay, so stabilized enolates do 1,4 addition reactions. These are extremely difficult to see. You really have to practice these reactions. And you might say, well, I get the concept. That's not that easy. Here's what's going to happen. On some sort of an exam, I'll write this product out, and then you have to envision what were the starting materials. Is that an aldol reaction, or a Claisen reaction, or a cyanohydrin-forming reaction? If you haven't practiced this, you're not going to see that this came from this 1,4 addition reaction. And this 1,4 addition reaction of stabilized enolates adding to enones is called a Michael reaction or a Michael addition reaction. So it's reminiscent of cuprates in terms of the selectivity, and you have to practice these. So in this case, if I have some sort of a base, I'll write the base out later. In this case, it won't matter because I don't have any ester groups. So let me just go ahead and write sodium ethoxide as my base. And we're going to have to follow this up with some sort of an acidic workup in this case. The book doesn't tell you that you have to use HCl for workups in Michael reactions, but I want you to put that because the book doesn't acknowledge the fact that you've got extremely acidic protons on these products, just like you did in the starting materials. So how do I work backwards from this? There's so many bonds here that could have been formed, right? What is going on? Did I end up starting here? Did I end up making an enolate at that position here and then do a 1,4 addition? Well, no, because if I made an enolate over here next to this carbonyl, it's not a stabilized enolate. Stabilized enolates add to enones. So in other words, you have to think through this. You cannot make this by making an enolate of cyclohexanone and then trying to do a conjugate addition reaction to this highly stabilized enone acceptor. That's not going to work because this would simply end up doing a 1,2 addition to the carbonyl. You need stabilized enolates, 1,3-dicarbonyl type enolates. And I'm putting this example because it's not exactly a 1,3-dicarbonyl. You should already know that cyano groups kind of act like carbonyls. They stabilize carbanions, kind of like ester carbonyls do. And so the way that you would make this is you would take this sort of starting material and you would add it to this ketone, this enone. That's the correct recipe. Because now you can deprotonate this and make a highly stabilized enolate, and highly stabilized enolates do 1,4 addition. They don't add to carbonyls, they add to the beta carbon. So that's the correct recipe. That's the correct starting materials for this Michael reaction. And again, it looks obvious when I draw this out for you, but when you're just confronted with that product and asked, how do you make this? If you haven't practiced this, it's going to just seem so difficult. You know what? I just noticed down here that for the Michael reaction, I'm saying that I would accept an H2O workup. Okay, I'll accept that since I put it on that slide. But you really use an HCl workup on these. Since I said it on the slide, and since the book uses H2O workups, I'll accept an H2O workup there on the exams and on the discussion sections. All right, so that's called a Michael reaction or a Michael addition reaction. And it's a great way to make carbon-carbon bonds, but it's hard to see the products when you're trying to work backwards. Let me show you one other example of a type of species that adds selectively to beta carbons of enones. So these stabilized enolates add to enones. Cuprates add to enones at the beta carbon. I'm going to show you one other special nucleophile that will add selectively to the beta carbon of an enone. And that is a thiolate anion. And this turns out to be an important reaction for biology because cysteine thiolate anions, that's one of the 20 ribosomally incorporated amino acids is cysteine. When cysteine forms anions, cysteine's very acidic, pK of about 9. So cysteine anions will do a lot of 1,4 addition reactions under biological conditions. So how do you do these reactions? Well, a typical recipe would be taking a thiol. In this case, I'm showing thiophenol. My gosh, does that stuff smell bad? Hard to believe. You can't explain the stench from that. I remember one time I bought, when I taught the Chem 52 lab here, I ordered a bottle of thiophenol so everybody could smell how bad thiols are. And as soon as the stockroom got the bottle, they called EH&S because it smelled so bad and had them take it away. So I never got a chance to get the lab to smell how bad thiophenol is. Okay, so you can see what's happening here is you're forming a new carbon-sulfur bond, and then the H, you're ending up with a new H over here. So the net effect here is you only need a catalytic amount of the base. And let's go ahead and talk about what's happening if you use catalytic sodium ethoxide or methoxide. You have to use ethoxide here because you want to match the ethoxide base to the ethyl ester. So what's happening is you start off by deprotonating this thiolate anion. Super easy to do under the conditions of under any conditions, because thiols are 1,000,000 times more acidic than alcohols. So very easy to make this thiolate anion. well, let me use a black pen here for this. And there's that sulfur with the lone pairs and a minus charge, and it's floating around with these enones. This enone is called ethyl acrylate. It's an ester of acrylic acid. And then this does that 1,4 addition. There we go. It's adding to that beta carbon, and I'll push the electrons up here to the alpha carbon. And that makes a carbon-sulfur bond, an extremely high yield. Now you'll get this enolate out of the reaction mixture that is very basic. That's not going to last very long because we still have the alcohol floating around. Let me just write it as HB for my proton transfer, but that's really ethanol that was generated in the initial step. You know, I blew that. I should have drawn the bond there. Let me backtrack. I apologize for that because you may have drawn it out. Just cross out. Whoa. And let me draw that bond because I'm going to break that bond when I deprotonate my conjugate acid left over from my first step. And that's the mechanism for thiolate addition. You just need a catalytic amount of base in there. And those are extremely efficient. Thiolates are so choosy. Let me be more honest with you about the thiolate anion. The thiolate anion does attack the carbonyl, but the O- selectively pushes the thiolate back out of the carbonyl. So you only get a stable product by adding the thiolate anion to the beta carbon. It's not that it's not adding to the carbonyl, but the product is only the product from sulfur addition, 1,4 addition of the sulfur. I think that this is not in the book. I can't remember. I think they might have had one example, maybe in the back of a chapter or something, but this is way more common. It's used as a way to join, to functionalize proteins, to make bioconjugate drugs in the pharmaceutical industry. You have thiolate anions all over proteins. You can put them in using genetic engineering, and then add whatever chemical group you want. So usually in the pharmaceutical industry, you put a thiol group on your protein, that's cysteine, and then you come along with your synthetic anti-cancer warhead, and you can join it onto any selective antibody you want. All right, the final piece de resistance for the whole enolate thing, the big shebang that they're trying to lead up to here, is a reaction called the Robinson annulation. In the 1950s, pause for effect here. In the 1950s, they had just discovered that there were these molecules, these tetracyclic compounds called steroids that had phenomenal potency. Not like aspirin, where you take like a handful of aspirin to try to cure your headache, but just a little pinch, just a microgram of steroid molecule could treat all kinds of diseases related to hormonal things. Testosterone, estrogen, corticosteroids, so potent because they act directly on nuclear receptors that control transcription. And so there was this big push to try to figure out how do we make some of these valuable hormones, because if they didn't do that, they had to go to slaughterhouses and extract them from like 10,000 cow ovaries or something like that. So the push was on to try to figure out how to make these just wildly complex molecules. And there was a reaction that was discovered by Sir Robert Robinson called the Robinson annulation that is beautiful for making these rings of steroids, like the AB ring system of steroids or the CD ring system of steroids. We have a standard lettering system here for these steroids like estrogen, testosterone. Okay, so here's the Robinson annulation. And it's extremely hard to see. It's extremely hard to see because what you do is you have to take a carbonyl compound that has very acidic H's. And so an example of that would be this 1,3-dicarbonyl. In some cases, you could have a benzene ring acidifying this, but the most common example would be this 1,3-dicarbonyl case. And when you mix these types of 1,3-dicarbonyls with enones, special types of enones that have alpha protons over here on the other side, you can get two types of carbon-carbon bond forming reactions in the same pot. So what's happening here is that you're generating a fused ring system, and what's happening is you're initially doing a Michael reaction, and then you start doing aldol condensations. And let's go ahead and walk through just some of the intermediates. I'm not going to draw out the whole mechanism. I think it's like 18 steps or some crazy thing if I draw out every single step. I don't remember. It's just not worth us walking through all those steps because we just talked about a Michael reaction. I'm just going to write down Michael right here. We just finished talking about a Michael reaction, so I don't really need to talk about, again, what's happening here. But you get the idea, right? If you add some sort of a base here, I don't have any esters here, so I could use sodium hydroxide if I wanted, and that would work. Or I could use sodium ethoxide, right? I just don't use sodium hydroxide if you've got esters. That wouldn't work. Okay, so you end up with some sort of a Michael reaction here where you're adding an enolate in and doing a 1,4 addition reaction. And so that makes an intermediate that looks like this. Here's my new bond. Makes a new enolate here. It's getting kind of crowded, and I'm not going to forget that methyl group that was at that enolate center. Let me draw that going up. So this is what you get after that carbon-carbon bond forming process of the Michael reaction. And you can see that bond that you just formed right here, that's the new bond right here. But now what's going to happen is we're going to have some proton transfers, right? We've got H's over on this side. We've got water floating around, other types of, I could symbolize this with HB, or we're not that worried about the mechanism, but we've got HB floating around that could reprotonate one side, right? You can see what can happen here is you can protonate this side and then pull the proton off the other side. It's all in equilibrium, pulling protons off. You could also deprotonate this side, but nothing's going to happen because it's not 6 atoms away from another carbonyl that can make an unstrained system. So as soon as you start doing these proton transfers, all kinds of proton transfers are occurring. I'll write exfers here to mean transfers. Right now, you'll end up with a new enolate species. You can't stop this from happening. You'll end up with another enolate floating around in that reaction mixture. And that enolate is 6 atoms away from another carbonyl. Whoa, don't do that. Let me give that a second to... Okay, we're back. I hope this lecture is recorded. So now we've got an enolate that is 6 atoms away from a carbonyl. Look at that. And that's going to do an aldol condensation under the conditions of the reaction. So really this is a two-stage process. It starts off with a Michael reaction. I'm not going to draw the steps for the aldol condensation. But then this does an intramolecular aldol condensation in order to generate this cyclohexenone product. So it's like you're generating 6-membered rings. Those map exactly onto testosterone. That's not the first products. The first products that were, I think it's, I don't want to say. Now we use a different method called the Torgoff estrone synthesis for industrial synthesis of ethinyl estradiol for birth control. But this was a real landmark for the ability to synthesize complex steroid molecules that have phenomenal potency. All right, the Robinson annulation, you got to practice that. There's going to be all kinds of variations, and if I ask you how to make that, if you haven't practiced it, it's just going to seem like this impossible task. Right, that's all for our enolate chapters. Chapter 21 and 22 were enolates. And so we're done with the enolate chemistry. It will be on exam 3. And when we come back on Friday, we're going to start talking about amines. Amine chemistry, ammonium compounds, acid-base chemistry, nucleophilicity. And amines are awesome because whenever I think amines, I think illegal drugs and legal drugs.